So should we start? I think so.
And let's start. So it's now 5 minutes after. So.
Okay, yeah, let's start. It's recorded anyway, so. Okay. So I will start to show the new intracranial EEG Montage Creator, which is included since the latest suite update. So now under applications, you can see that there are now 2 Montage Creators. So this one is the exit.
If you're
sorry. I have to
sharing your screen, we don't see anything.
Sorry. So can you see my screen? I think so, yeah.
Yes, now we can see it.
Perfect. So now, since the latest suite update under applications, you will find 2 different Montage Creators. So this one is the existing one you already know, which is for EEG and EMG and all this stuff. And now we have a new one, which is for intracranial electrodes. So up to now it's for ECOG, and we will extend it to also support stereo EEG electrodes. So just a short overview about the timeline. So in the summer update, we released the intracranial EEG one for ECOG. And in the next update, there will be another one, a new Montage Creator for the g.Pangolin. Yeah, and maybe later, someday we will also replace the existing EEG one with a new Montage Creator for EEG. Yeah, so let's start the application. So this is the new EEG Montage Creator. So what you can see here, you have 4 different options to start creating a ECOG montage. So the goal of this tool is to be able to place electrodes and then create a montage which can be used for visualization in g.HIsys or g.BSanalyze. And the default selection is that you want to create a montage based on this MNI template brain. So this is the use case if you don't have any data for your, so no MRI or no CT data for your subject. So with this option, you can use the template brain and just create your montage, not subject specific, so just with a template brain. This is possible for everyone at any time, so you don't need any additional data. Yeah, and then there are 3 more options which I will explain later on. So now we have this MNI template brain already available and loaded. And here you can see the workflows. So this is basically the things which you are able to do now. So one workflow which you can do is to place electrode grids, and another one is to get electrodes from CT. So, but now we have our template brain and we just want to place electrode grids. So for example, we want to visualize some motor activation later on in g.HIsys. So we can say, okay, we select a grid from the grid database. for example, this 20 channels grid, and then we can edit. And here we can now interactively move the grid on the brain and place it, for example, here on this motor area. So now you can see that also the grid snaps onto the brain, and yeah, you can place it anywhere. Now we can add another grid, for example, somewhere else. And yeah, so you can easily build up your montage. It's even possible to scale the grids or to change the rotation. And you can also exclude channels if you don't want them. So now we excluded these two channels. And it's also possible to define a reference channel and a ground channel. So if you are familiar with g.TEC, this is basically the same like the g.TEC Montage Creator. It's just in 3D. And instead of a background image, you're using this 3D template. Here you can also change the grid ordering so that you set the channel numbers accordingly. And yeah, so now, for example, we want only these 38 channels, and we are happy with the placement. And then we apply this by going to the next step. So you can see a workflow always consists of a certain amount of steps, which you can do one after the other. And now we are also already finished. So it says, okay, this workflow is finished. And then we can already save the montage. And a file will be created, which is by default, it's placed in g.tec Montage Creator, and also a montage definition report is created. And here we have our montage now. It's an XML file, and this file can be used in g.HIsys and g.BSanalyze for visualization purposes. So yeah, so that's one use case. So you just want to place electrode grids on this template brain to just get the raw visualization, but not subject specific. Another possibility, this is the second one, is to start a montage, a new montage from an image. So it starts with a blank white image, and you can basically do the same. So you can also place grids, and this is basically exactly the same like the g.TEC Montage Creator from the existing g.TEC version. And what's the use case now to do this to use this mode? It's, for example, if you want to, you can use it during the surgery, for example, and load an image of the craniotomy. So something like this. You can also use a webcam. You have access to a webcam. Then you can take, for example, an image of the craniotomy and then quickly place the electrode grids. Like this. Then we can do a little bit of scaling. And then you can save it and use it, for example, with g.HIsys to do some real-time mapping. And of course, you can also load any background image, like in g.TEC. You can also load some schematic image. Just in 2D instead of 3D. So like this, for example. You can also use this like it was in g.tec. And then you can also apply this and save your 2D montage now. Here you can always also set the subject name and the montage name. So we could save it as 2D montage, test subject. And yeah. Now we have this test subject underscore 2D montage available. So all these steps here, it's the same like going here from file and new. So from MNI, from image, so it's the same. And these are just generic things. So you don't need any patient-specific data, but often you want to get accurate electrode positions. You want to get the real positions of the electrodes which were implanted. And one possibility is to use this free surfer option. So let's start it. And this allows you to import data from FreeSurfer. And what is FreeSurfer? I can show you an image. So FreeSurfer is a widely used tool in this field. I think it's the best tool. There's no real alternative to this. And you simply need a T1 weighted anatomical MRI image. And then you run this tool. It's basically a command line tool. And then it takes up to 24 hours to do a lot of processing. And it will generate an output folder with many different files. And like you can see here, one output is, for example, a really accurate and nice 3D model of the cortex. And you even get these anatomical atlases where you can see the gyri and so on. So it's pretty nice, but it takes many hours to process. So like you can see here, it's only available in Ubuntu and in Mac on iOS, but yeah. So now I'm working on a Windows machine, so I'm using a virtual machine, and it's just like you can see here, it's just a single command, and you input your MRI image, and then you have to wait for many hours. And finally, you receive such an output folder, which contains a lot of files. And in the Montage Creator now, we can simply load this output folder. And you can see that all the files are recognized. Expect this one. This is a head model where you need to run an additional command to get this, but we don't need it for ECOG. And now we can press import and import the output of FreeSurfer. And this is now really a subject-specific data. So we're able to localize the electrodes later on like they were really implanted. So now we loaded it. And you can always, in the Montage Creator, you can do this at any time. Go to Tools and Preview, and then you show how's your montage looking at the moment. So now we have a cortex model available, and we have an MRI image available. So after importing this stuff, this is the data we have now, and we don't have any electrodes yet, obviously. What's also pretty cool when using FreeSurfer data, you get these colorings where you can see all the anatomical regions. It's pretty nice. And all this stuff can later on be used for visualization, for example, with the 3D scopes in g.HIsys. Yeah, so let's continue. And now we could, for example, also place electrode grids just roughly on our subject-specific brain, but we don't want this. We want to get the electrodes now from the postoperative CT, because these are really the positions which were implanted. So now we have to do more steps to finish our montage. And the first is to compute a brain hull. So you simply have to click run. And then this step produces a hull which covers this brain. And we need it later on to compensate the brain shift between the preoperative and postoperative data. Because the MRI, which was used to create this cortex model, is preoperative data, and the CT, which contains the electrode locations, is postoperative data. Therefore, we have to compensate the shift, the brain shift. So now we have a nice brain hull covering the cortex. So we can continue with the next step. And this is the CT registration step. And like you can see here, we have the cortex and the MRI. And now here we have the option to load our CT data. So here I will show it here. So this is a postoperative CT, and you can here see these bright spots. These are the implanted ECOG electrodes. So now we import this data. And now let's move this. And now we only see the MRI again. And that's because the MRI and the CT are in a total different space, because they were acquired with a different scanner and so on. And therefore we have to align these pictures. So the first thing we can do is to initialize the transform. So this will just roughly align the images. So now they are approximately in the same space, but they are not perfectly aligned, like you can see here. And sometimes the images are really flipped by 180 degrees or something like that. So you can help the algorithm a little bit to do some manual transformation beforehand. So here you can manually align the images a little bit beforehand. And then you simply have to click run, and then the automatic registration process starts, and both image modalities will be registered. So we can also, so like you can see, it moved up, and now it gets better and better aligned over time. So you get also a real-time update of a certain amount of iterations, and here you can see in the status bar, you can see the current iteration and the result. You can always stop in between if you are already happy with the result, or you can change some parameters, for example, the number of voxels which should be included in the registration, and rerun it, for example. And it's all, of course, also possible to use any other tool to do the registration. And then you can simply load an already registered to CT like this. So here you can see it's pretty nice registered, and use this. That's also possible. And yeah. So like you can see now the CT and the MRI and our 3D cortex, they are pretty nicely aligned. So let's go to the next step. And in this step, our goal is to segment the CT electrodes. So like you can see, these bright areas were segmented, and we receive basically the electrodes and some cable artifacts. This is a default threshold which was chosen, so you can also vary, change the threshold and get the electrodes. Like here, so maybe a little lower. Yeah, and of course you have this many artifacts, so we want to remove it. So in this step we can crop all this unwanted CT data. So because we only want the electrode locations. I will also remove now, you can see this is a grid, this is an implanted grid, this is a strip, and so on. I will remove everything except one grid, because otherwise it would take too long. So crop it. And here we get also a little history. And if we remove this entry, we can restore it if we made a mistake. So to remove this. So now I'm happy. I extracted my grid, which I'm interested in. And now I can go to the next step. And here we have the possibility to automatically detect electrodes from this surface. So just click run, and now you got all these electrodes automatically detected. So, and of course this detection is not perfect. So now it worked perfectly, but it maybe some electrodes are missing, or there are too many electrodes. So in this step, you can move the electrodes a little bit, or you can remove detected electrodes or manually add electrodes if they are missing. So in this step, you have to ensure that all electrodes are available which were implanted, or which you are interested in. So we can go on. And like you can see here, so in this control panel, it's similar to it's the same like in the 3D scopes. We can, for each step, control the visualization and decide what we want to see and how. And here we see that for ECOG, we now have these original electrode positions available. And original means that these are the initial positions from the CT. But you can see that the positions are a little bit inside the R3D cortex model. And that's because of the already mentioned brain shift between the post and preoperative data. So in this step, we can compensate this and project the electrodes. So now we projected them and we get a new entry. We can even switch between the different positions. And these projected positions are now, fitting the cortex quite good. So now this is the last step. So now we detected our electrodes from the CT, so the locations are already good. But like you can see here, the electrode numbers are not right now. So in this step, we can assign an electrode grid to this. So this was a 20 channel grid. So we selected from our database. And now we can link the detected electrodes and our grid. So we can just select the electrodes accordingly. And then click apply. And now we grouped the electrode positions to a grid, and we even get the corresponding grid shape. And now here we have an electrode grid group, and we can go for it. And if we have many electrode grids, we can change the ordering and change our montage and the channel numbering accordingly. So now we're ready and we can finish our workflow and save our subject-specific 3D montage. Yeah, so now I didn't change the montage name, but it's now a 3D montage. So that's the third option, what you can do. And this is usually the case what we do with, for example, the studies with Dr. Kamada, where we need accurate information. So we do all these processing steps for each subject. The last possibility is to use this other importer. And this is a very generic one. And this allows you to load any other files. So because maybe you don't want to use FreeSurfer because it takes a long time and you don't need these very nice results. You are happy with a more rough 3D model, then you can use this. And it allows you to set the cortex model by using a surface file. So any surface file. So we support 3 different formats: the g.tec format, the STL, and the object format. These are widely used 3D formats, and you can load any mesh to set the cortex. So yeah, you can use any other tool, convert it to one of these formats and import it. And another possibility is to load an image. So of a segmentation, so like this. So this is an image of a gray matter segmentation. So it looks like this. So the gray matter is white and the rest is black. And you can easily get this image with MATLAB. So there's a toolbox which is called SPM. It is a well-known toolbox for fMRI processing and analysis. And this toolbox also allows you to import MRI image and create these this gray matter segmentation image. And this is way faster. It takes about 5 minutes. And then you get this gray matter segmentation. And here we can import this segmentation image. And you can see that it is automatically converted to a 3D surface. Now I only set it for the left hemisphere, but this image contains both. So we have to only set, we can say that we don't have separate cortex hemispheres. So yeah, and like you can see, the result is good, but there are many artifacts. It's not perfect. And the cerebellum, for example, is included. So it's not possible to place grids, for example, at the temporal base by using this rough model. But for some motor area studies and so on, and if the time is limited, you can use this. And again, we import it and we have our workflows available. And now we can, for example, place electrogrids on this model. And now we need again a hull, because we can't place the electrode grids directly on this cortex model. So we need a hull which covers it, so we can smoothly move our electrode grids. And then we can basically do the same like with the MNI option on the template brain, but with our subject-specific brain, or any brain we are interested in. So now here again, we can place our grids accordingly. Yeah, so that are the options which are possible with the intracranial EEG Montage Creator. And I think Patrick will show you the new features in g.HIsys, and we will see how we can use these new montages in g.HIsys to do some nice visualizations. Yeah. And along with this Montage Creator application, a grid library is installed, and it is installed under Documents, g.tec. Now we have here this electrogrid library available, where all this grid information is saved. Yeah. Yeah, that was the intracranial EEG Montage Creator. Someone has questions.
MJ, do we, or can you provide us some files for this FreeSurfer import, for example? Or are there any examples included that we can try it out? Because I tried now recently the standard procedure with the image and with the brain, the 3D brain, but I couldn't find a FreeSurfer file or something. So
yeah, sure, I can.
That would be great, because then we can.
Just let me know where I should put it. I can put it on my Exchange, or I don't. Or do we have some other places?
Yeah, I don't know. Exchange also would be fine, but yeah, we can discuss it later on as well. But yeah,
yeah,
only
that's no problem.
to play around a little bit with it.
Yeah, sure. So we have plenty subjects available from Dr. Kamada, I think 30 or something like that. So I can upload some data.
So if there are no more questions, I'm going to continue with the g.HIsys introduction. So thanks, Michael, for the introduction of the iEEG Montage Creator. And yeah, I'm also going to share my screen. Okay, so the g.HIsys also got an update with the recent summer update for the g.tec suite. So again, as every time, you see the update in your updates tab of the g.tec suite, and you also can read the notifications what changed to the g.HIsys. So actually, what changed to the g.HIsys is that we now support the Tobii Pro Classes 3 eye tracker. Yeah, basically the device stays the same, it just gets a new, more modern look. The way how to use it is still the same. So we have the synchronization port on the Tobii Pro device, which can be connected to the g.tec amplifier, to the Nautilus USB amp or the high amp. And then you can synchronously record EEG and eye tracker data and analyze the data together in 2 steps. The first step is in the Tobii Pro Lab, and the second step is then afterwards in the g.BSanalyze. Yeah, I just want to show you how the model looks like. So it's Tobii classes. So this is the template for it. We do have a sync port output, but this is not working currently. So we need to activate this. Once this sync port is working, we do not need the hardware cable to connect the Tobii classes and the amplifier, but currently this hardware connection is still needed. So when we double click the block, one important thing which is different to the Tobii Pro Classes 2 interface is that we can decide here if we want to calibrate the device when starting the model or not. So having this option enabled requires you to have the calibration card in front of you when you click Run of the Simulink model to perform the calibration process. If you don't have it unticked, you're going to use the calibration, which is stored to the device. Yeah, beside that, everything basically stayed the same as for the other interface. We cleaned the interface a bit up. So before we had all the eye tracking data also imported to the Simulink, but basically there is not too much use of this data because you would need the scene view video. Without the video, the data is completely meaningless. And now we decided to make the interface a bit more or easier to understand, basically. And yeah, so we just kicked this output, but this is available in the Tobii Pro Analyze software. You can access the data from there. Okay, so this was the point for the Tobii Pro classes. And the next for the HIsys, we added a mapping toolbox. So if we open the Simulink start page and search for mapping, we now have 2 different mapping Simulink models. One is for the CSAP mapping, and one is a central sulcus mapping using SSEPs, somatosensory evoked potentials. Yeah, just gonna show you the CSAP mapping. So CSAP stands for cortical evoked potentials. So basically what is done in here is that you have a g.HIsys Pro, which is stimulating some sites on the cortex. And then you want to highlight areas in the brain which are connected to this connected to this area where you stimulate. So the model consists of a pre-recorded data file. The file is added, or the data from the file is loaded to the Simulink model. Then we basically extract the EEG and the trigger data. We do common average reference. We extract bad channels. And then we trigger the data for the onset of the stimulation, basically, of the eStim Pro. And we form an average of all this stimulations. So as far as I remember, yes, we have a window length of 350 milliseconds with a 50 milliseconds pre-trigger window to be able to baseline correct the data. And then we're going to search for this N1 peak. And the N1 peak in the EP tells us if this region or if the electrode is functionally connected to the stimulation spot. So the N1 peak is searched in the EP, and then it will be visualized in a 3D bubble scope. And let me just start the bubble scope. So you see that we have here our brain inserted, and this is where the tool of MJ comes in. So basically, we need the brain model So for this demo data, the brain model is already loaded or already linked to this model. But if you don't have pre-recorded data, and if you want to use it with an amplifier, it's necessary that you run the iEEG Montage Creator to create this brain model, which includes the information of the electrodes, the grids, and also the anatomical landmarks, the atlas of the gyri. So let's take a look what happens when we start the Simulink model. Maybe I'm gonna disable the control to get the bigger view. Let me get the Simulink model. It's not that important. So I'm gonna start the Simulink model, and the data is then processed. And we see here the two yellow spots are the stimulation site. So these two electrodes were used for g.HIsys Pro and for the switching unit to stimulate the cortex. And all the red bubbles that we see here, these electrodes show in the EP N1 response. And this tells us that these areas or these electrodes are connected with this brain site. So we're going to see if we stimulate here, this region is interconnected to the spot, but we also find in some other grids, for example, here we find something. And interestingly, on the other side of the brain, there are also some electrodes which shows a connection to the stimulation site on the different side or the other side of the brain. So the model also comes with a vector scope, which just visualizes the EP of the recording. And for example, if we take a look at this channel here, we see the evoke potential, and we can use the measure tool to measure latency and the amplitude of the peaks. Okay, so this was the CSAP, mapping tool. So basically, this is just there for demonstration purposes. But if someone is interested in doing CSAP, they can basically just replace the real-time clock and the two file block with an amplifier, and then they need to set up the channels accordingly and have the brain model, and then they can do the same CSAP processing as we do for the offline processing. Any questions for this CSAP mapping? Otherwise, I'm gonna continue. Okay, seems that there are no questions, so I can continue with the next mapping tool, which is the central salt mapping tool using somatosensory evoked potentials. So we also have pre-recorded data, which is coming from a median nerve stimulation. And as before, data is coming in. We select EEG and the trigger data. We filter the EEG data. We also then trigger the data to the stimulation onset point. We form an average. And then what we do in here for the processing is that we check the phase detection. So we have a phase detector, which shows if there is a phase shift or a phase inversion in our EP. This tells us then exactly where the border of motor and sensory area in the brain are. So we have here this phase detector, and then we check if it is a positive peak or a negative peak. Yeah, the positive peak and the negative peak will get the separate bubble color, and it will be visualized in the bubble scope. So let me again show the scope first by double clicking the bubble scope. And we see, as also MJ said before, we can color the brain with this anatomical landmarks. And we see here on the right hemisphere, so we have a left hand median nerve stimulation. So on the right hemisphere, we expect something to happen. And we see here the blue area here is the motor area, and the red one is the sensory. And we have a grid which is placed above this region. So let's check what's happened when I start the Simulink model. So we see that above the electrodes, we will get some bubbles, and we see that the blue bubbles detected or classified evoked potential, which is coming from the motor area, and the red bubbles detect EP, which is coming from the sensory area. The different size of the bubble is basically the difference of the amplitude of the peak. So basically, you have a maximum and a minimum, and the difference between these points is the size. And if it's going from negative to positive, then it's one class, and if it's going from positive to negative, then it's the other class. But we see basically that we can pretty well classify if that we can identify the regions in the brain with this online processing methodology. Sure, there are some misclassified electrodes, but you see also that the size of the bubble is pretty slow, so the algorithm was not sure if it's now a sensory or motor EP. So, and also interesting is that we do not find any bubbles, or if we find they are rather small, on any other side. So this face detection algorithm that we implemented is really capable to just detect the regions that are involved in the motor sensory task for the subject while doing the MNI, the medium nerve stimulation. Okay. Any questions to that, to the mapping tools? Yeah, as I said before, also the central sulcus mapping tool is currently offline tool, but yeah, you can replace the from file block with the amplifier, and then you can do the central sulcus mapping with either online or with data that you recorded from your subject, but then you would need the brain model and the grid information from the recording that you did using the iEEG Montage Creator that MJ demonstrated before. So if there are no questions for the g.HIsys, I just continue with the g.BSanalyze. In the g.BSanalyze, we added a 3D visualization of montages and anatomy and brain model integration. So let me show what this means for you. So we have the G1 creator. And you recognize that there is a button which says show with G result 3D. So for example, if I load a montage, a standard montage, for example, the 64 G Nautilus one, we have all our positions defined here. And now I can click here, show with results 3D. It will take a bit. And then we get this overview of the montage. So we have all the electrodes with some gray spheres and black font saying with the electrode name. And then we can rotate the brain and take a look which electrode sites we actually defined in our montage. We also have the overview from right, left, and from top. And we can also change to a 2D view, which will basically, so this looks exactly the same as in the Montage Creator, but in the 3D view, we can, for example, also change from the 3D scalp to the 3D brain. And then it will show the cortex visualization. For those EEG montages, we currently use the general brain model, the MNI brain model, but it's also possible to load the brain model. I will show it afterwards with the Cortiq importer. I just want to show you the options. So basically what you can do is that you can change the sphere color. So if you want to have pink spheres, you can change the radius, you can change the font size, font color, and maybe we want to have a nice dark blue font. Yeah, we can modify the size and the font a bit. And we can also export the graphics with a different resolution, so up to 1200 dpi. which is super high quality. For demonstration purposes, I just used the 150 dpi so that it doesn't take that long. And we can decide if we want to have all axes, so this freely rotatable one, and the overviews, or if we just want to have the main axis, which is this plot here. So I'm gonna export all of them. I'm gonna call it channel export. Gonna click export, and export is done. And yeah, so this is the file that it just generated, and this is how it looks like. So it keeps the orientation of the 3D rotatable one, and also includes the overview brains. So, good, so that's it. Something else, yeah, here we can say which overviews that we want to have. So now I also check the one from the ventral. Now I could get also a view from the bottom side of the brain, but it doesn't make too much sense for the EEG. That's the reason why it's not shown in this mode. So what else do we have in the settings? Yeah, we can play around a bit with the transparency of the scalp and the brain, and we can decide if we so how we want it to be rendered, if it's rendered for hardware, software, or the hardware basic. So this could make a difference in speed on some machines. Yeah, we can also go ahead and say, okay, we want to have a new montage, and then, for example, we have a super high dense grid. For example, the 122 channel cap. Then we can go ahead and also use these intermediate positions here. We select the electrodes that we want to have in our montage. And then again, we click Show with Result 3D. And then we get the overview and the 3D visualization of the montage that we just created in the Montage Creator. Okay, so now I want to show you how you can import patient-specific brain models. And this is currently only available for Core.tec montages. So I need to import the Core.tec montage at first. Core.tec test montage. So this will import all the channel information from the Core.tec with the grid information. And now we can import the brain model. So the test brain model. Okay, so this is loaded, and then we can say Show with Result 3D. And so this is just a 2D overview as we know it from the Core.tec Montage Creator. But we can switch the visualization to the 3D view. And then we get the 3D representation of the montage that we just created. We also have the grid information included here, so we know exactly where the grid was placed, and we have the electrodes here. We also have the overview from from left, from right, top, and bottom. And Yeah, again, we have the same options dialog. We can change the sphere radius, we can change font size, font color, and so on. We can export the image, and this could help to identify or to make it easier to understand the analysis. If you know exactly, okay, this grid or these electrodes are on the spot of the brain, and then you get an analysis report, which is then easier to maybe identify or understand if you have the montage next to the data. So are there any questions concerning the 3D visualization within the g.BSanalyze? So I see that there are some messages in the chat. Okay, so this is related to the test data for the iEEG Montage Creator. So it seems that there are no questions left. Yeah, then we can stop the training here. Thank you for the attention. I will send the signature sheet to you in the next hours, and I'm gonna split it for all the sites. So there will be one sheet for Graz, one sheet for Upper Austria, and there will be a separate one for Christie and for the US team. Okay. Thank you so much for your attention, and enjoy the rest of the day.